In distributed systems, uptime often hinges on how fast we can redirect traffic to a healthy infrastructure when failure strikes. Vultr Reserved IPs gives us the ability to reassign traffic between instances, but that requires a manual step. If your instance goes down, you need to intervene to reassign the IP. To eliminate that operational friction, we can combine Vultr Reserved IPs with dynamic BGP route advertisement. This transforms it into what we call a floating IP behavior, a setup which automatically shifts IP to an active instance based on availability. Hello everyone, I'm Sanskriti Harmak, a developer relations at Vultr, and in today's Tech Talk, we are going beyond static infrastructure to explore how BGP and Linux routing daemon can create intelligent and self-healing network with Vultr reserved IPs. So, to experience it all in action, let's jump right into it. Reserved IPs are a solid abstraction for detaching your application from any specific instance, but they still rely on manual reassignment during failure, which introduces downtime. With BGP in the mix, we move that decision making into the network layer. Each instance advertises itself as the destination for the reserved IP, and if one instance goes down, another can take over the route instantly. The IP continues to be reserved from Vultr's side, but it behaves as a floating IP because BGP tells Vultr Edge Router which instance is currently reachable. This reduces recovery time from minutes to seconds and supports automatic failover over stateless application, microservices, or high availability clusters as long as the instances are deployed in the same region. Let's now break down the key components that make this setup work. Reserved IP is still at the core. It's what clients connect to. But instead of binding it directly to an instance, we attach it to a dummy network interface created inside the operating system. That dummy interface becomes the anchor point for route advertisements. To tell Vultr's network which instance currently owns the route, we use BGP. The Border Gateway Protocol allows the instance to speak directly to Vultr's edge router. And to actually speak BGP, we use the BER 2.0 daemon, a lightweight, high-performance routing engine that advertises reachability for the reserved IP via the dummy interface. This means whichever instance is running BERT and has the interface up will automatically become the new destination for all the incoming traffic. Let's talk about what makes BGP-backed reserved IPs a critical upgrade for high availability architectures. This setup brings failover logic to the protocol level, not just in cron job or health check script. BGP speaks directly with Vultr's network edge, so the router knows exactly where to deliver traffic for the reserved IP at any given moment. So whether you're running a primary-secondary setup, a rolling update system, or live migration of workloads, BGP plus floating IPs make sure that the network keeps pace with your app availability. Now that we understand the theory and architecture, let's walk through a practical demo. We'll start by provisioning multiple instances in the same region, attaching a reserved IP to the dummy network interface, and configuring BERT to advertise that route via BGP. You'll see how traffic switches automatically as we bring interfaces up or down across instances. We'll also look at how to prioritize failover order using BGP Prepending and validate everything with live ping tests. Before we dive into the configurations, there is one important prerequisite that you need to take care of. That is enabling BGP on your Vultr account. BGP is a core part of this high availability setup. However, it is not enabled by default. To request access, head to Vultr Customer Portal and navigate to the Networks tab and select BGP. This opens a form where you can submit your request. In the form, you will be asked to provide details such as the reason behind requesting for BGP, your preferred routing method, and whether you are announcing your own prefixes. Once submitted, the Vultr team will review the responses and grant you the access. I have BGP enabled on my Vultr account. But if it is your first time, please refer to the BGP product documentation where we have curated a list of a step-by-step guide that will help you with how to request access for BGP, understand ASN assignments, configure RPKI, add prefixes, and learn more about your access credentials. Let's navigate back to the Vultr customer portal to continue with the setup. Head to the compute section on Vultr and click on Deploy Server to provision 2 Ubuntu-based instances. We'll start by selecting a compute type. We'll go with shared CPU and then choose a specific region. Further, we'll pick a compute plan that satisfies our resource requirement. Then we'll select a base operating system. For this demo, we'll go with 24.04 Ubuntu. Then select an SSH key for secure remote access. You can optionally configure a startup script or add a firewall group if needed. Because we are setting up a high availability environment, will increase the number of instances to 2. You can also add multiple nodes to this high availability setup. Just make sure that all of them are deployed in the same region. Next, we'll provide a label to our instances. From the additional features, we'll configure our instance with IPv6 address alongside IPv4. We'll also select a non-root user with sudo privileges. Now that everything seems to be configured, click on Deploy, and this action will launch 2 Vultr Cloud Compute instances deployed in the same region. Now that both of our instances are up and running, open the management page of one of the instances. Because we have BGP approved for our Vultr account, you'll spot a BGP dedicated section here. This will include details such as private instance ASN, neighboring IPv4 and IPv6 addresses, Vultr ASN, as well as BGP session password. We'll use these configuration values shortly while setting up BERT on these instances. We have configured this environment for Vultr Cloud Compute instances, but if you're working with Vultr bare metal instances, then you can provision it in the same way. The only difference lies in the BGP configuration values for parameters like Vultr ASN and IPv4 and IPv6 address for Vultr bare metal instances. Next, let's head over to the Reserved IP section present under Network tab on Vultr. Here, we'll provision 2 reserved IPs. First, we'll create an IPv4 reserved IP deployed in the same region as that of our instances. Then, we'll give it a label and click on Add. Then we'll create another reserved IP, which will be IPv6 and deployed in the same region as that of the previous reserved IP and the instances. We'll again provide a label and click on Add. If you would like to know more about how Vultr Reserved IPs work or would like to convert an existing instance's IP address to a reserved IP, then please refer to our tech talk titled Getting Started with Vultr Reserved IPs to gain more context. Now let's SSH into Demo Server 1 to execute next phase of configuration. We'll start by setting up a virtual interface for the reserved IP. This allows us to bind IP to the interface that we control independent of the instance's default network interface. We'll be using a dummy interface, which is a non-physical interface that holds IP but doesn't send traffic unless explicitly routed through it. Now we bring it up and assign our reserved IPv4 and IPv6 addresses. These are the addresses clients connect to, and this interface will act as an anchor point for our BGP route advertisements. Let's now verify that the IPs are attached correctly. As we can see, both our reserved IPv4 and IPv6 addresses are successfully binded to the dummy interface that we just created. Next, we'll install BGP routing daemon BERT 2.0, which speaks BGP from our instances to Vultr's router. Before we configure BERT, let's allow TCP port 179 through the firewall. This is the standard port that is used for BGP sessions. Let's now back up the default BERT config so that we can restore the original config if something goes wrong. Now let's replace its content entirely with a custom configuration that enables BGP routing for our reserved IPs. Router ID is the unique identifier for the router that expects the main IPv4 address of the instance. Protocol device enables BERT to monitor all the available network interfaces on the system. This is required because BERT should be aware of the dummy interface HAIP that we earlier created. Protocol Direct, on the other hand, tells BERT to announce all IPs bound to HAIP interface directly to BGP. Protocol kernel ensures that all the IPs managed by BERT should be shared with Linux kernel routing table. Whereas protocol static is required even if it is empty. It is a placeholder and is mandatory for BGP to enable static routing for IPv4 and IPv6 addresses. The Vultr IPv4 protocol block expects some BGP configuration values, starting with local S that needs to be supplied with private instance ASN, whose value can be retrieved from the dedicated BGP section present on the management page of the provisioned instance. Next, we have source address, which is set to the main IPv4 address of the instance. Then, we are supplying the neighbor IPv4 address along with remote ASN for Vultr Cloud Compute instance, which is fixed as 169.254.169.254 and 64515 respectively. The BGP session password can also be retrieved from the dedicated section of BGP on the instances management page. Similarly, we can configure the Vultr IPv6 protocol block by supplying the private instance ASN, the source IPv6 address, and BGP session password. After configuring everything, save the file and exit from it. Once we have set up BERT 2.0 on our demo server 1, we can restart the service to apply the changes. Let's now verify the status of BGP session. First, we check for IPv4. As we can see, the state is up and BGP session state is also established. This means that we have successfully formed a BGP session with Vultr's router. Now let's verify the same for IPv6. Here as well, we have received the BGP session state to be established. Next, let's make sure that our routes are advertised correctly, especially through the dummy interface that we set up earlier. In the output, you should see the reserved IPv4 and reserved IPv6 addresses binded strongly to the HAIP interface that we created. Let's test the connectivity by simulating a failover scenario. I've opened two terminals side by side. In the first terminal, we are pinging reserved IPv4 address, and in the second terminal, we are pinging reserved IPv6 address. While these pings are running, we bring the dummy interface offline, which will simulate our instance going down. As expected, the pings either stop or are unable to reach the destination. Since reserved IPs are no longer bounded to any interface, it becomes unreachable. Now let's bring back the interface. As you can see, the pings resumed automatically, confirming that traffic could be dynamically rerouted as long as the BGP session is active and the interface is up. Let's now set up these configurations on our second instance, which we deployed in the same region as that of our first instance. I've set up HAIP dummy interface and configured BERT 2.0 on demo server 2. Now let's talk about traffic control. When using BGP in a high availability setup, we can control which instance receives traffic by adjusting AS path lengths. AS path is a list of autonomous systems that a network route has passed through to reach a destination. BGP route prefers route that has shortest AS path. By prepending the local ASN, we can artificially elongate the path and deprioritize a specific instance. For that, let's configure demo server 1 as our primary instance, which receives all the traffic by default, and demo server 2 as our secondary instance, which receives traffic when demo server 1 is either down or unreachable. To do this, we need to reconfigure BERT 2.0 on demo server 2. In both Vultr IPv4 and Vultr IPv6 block, we are modifying the export statement with BGP prepend filter to reduce its routing preference. This tells BERT to prepend the local ASN when we are advertising the routes. Let's save the changes and exit from the file. At this point, we have the HAIP dummy interface active on both demo server 1 and demo server 2. Let's now test the traffic priority by simulating a failover scenario again. For that, ping the reserved IPv4 address on terminal 1 and reserved IPv6 address on terminal 2 and bring down the HAIP interface on demo server 1. As you can see, the packets that were failing previously when HAIP dummy interface went down on demo server 1 is now successfully reaching demo server 2, which is our secondary instance. This shows that demo server 2 has successfully taken over and is now serving the traffic for the reserved IP bounded to HAIP dummy interface. And that's how you can build an automatic failover scenario using Vultr Reserved IPs, BGP, and BERT 2.0. One important thing to keep in mind though is manually created dummy interfaces and IP assignments are not persistent across reboots. To ensure that interfaces and reserved IPs survive reboot, configure them using systemd networkd or similar persistent networking tool. To learn more about how to achieve persistence, please refer to the supporting guide linked in the description below. To wrap up, we have seen how reserved IPs build the foundation for IP mobility and how BGP extends that with dynamic route-aware failover. By running BERT as a BGP daemon, each instance can advertise its availability for a reserved IP at the protocol level. This design supports high availability clusters all without downtime or DNS updates. If you would like to replicate this setup on Vultr, you can get started by claiming $250 in free credits on a new account using the promo link attached in the description below. Thank you so much for joining this tech talk. We hope it helps you build resilient and self-healing architecture on Vultr.